in this video we're talking about electric field due to a surface over a surface, or an infinite surface. Basically, not really a surface, but a plane. Electric field over an infinite plane. And somebody's messaging me on Steam, but basically, this is what we're working with here. If you want to get sort of a visual, we have the XYZ axis, and we have this plane, an XY plane, and this plane actually extends in both X directions and both Y directions. It's actually infinite in that respect, and we're just finding a point above the plane somewhere. So we just, any point we want above the plane, we just shift our coordinate axis so that point has coordinates 0, 0, H. You know, I say it might sound kind of weird saying an infinite sheet, but basically you do these sort of things because it's an approximation, because things turn out a little differently if it's not an infinite sheet. You have to take different things into account, and this is a good approximation, you know, for if you have a plate, like a copper plate or something. So this is our geometry. This is the point we're interested in, 0, 0, 0, 0, H, and we're going to be working in polar coordinates. I use rho, that's a P, I know, but I use rho as the R for polar coordinates. That's the angle. And this is going to be our vector R from the source of the charge to the point. Now, if we go back to this, if you remember from the previous video where we did a line charge, we had this differential element of electric field equal to this, where A sub R is in the direction of this R right here, and yeah, this is the magnitude of that R, this is the differential charge, and this is the constant that's always in the denominator. Also, we said that the surface charge was equal to this. This is a surface integral. It's the surface charge density over the surface, and in this video we're going to be assuming that rho sub s, surface charge density, is constant. Put these two guys together, boom, we get this guy. This is pretty much what we had last time, and it's the same sort of type of approach. We have to get each part of this integral and just put it all together. So we're going to get R first. So if we get, let's see if I still, oops, R, come on, bold, there we go, R, bold because it's a vector. Let's see, well, what's our R going to be? It's this guy, right? So what coordinates does that have in the polar coordinate system? Now, well, obviously it's going to have a z component of H, and I never like to say obviously, because sometimes, like, it'll be in a book, and it'll say, this is obviously that, and sometimes it's just like, nope, no it's not. Like, to me, I feel really stupid when people say obviously and I don't get it. And like, sometimes that happens, like, in the solutions manual. Like, I got a solutions manual, and I look at one of the solutions, and it says straightforward. That's it. Okay, this is in one of my math classes. It said straightforward, and I was like, wow, I must be really, you know, I felt really stupid because I mean, I got it eventually, and I was like, oh yeah, that is straightforward. But I'm thinking, like, you know, it's a solutions manual. You put a little bit more than straightforward. Anyway, I'm getting a little off topic, but like, that's crazy. But yeah, well, so we have a coordinate in the z direction of H, and we're going to have a coordinate in the rho direction. But the interesting thing to note is that the coordinates are not going to be just rho in the rho direction and H in the H direction. It's actually going to be, I'm going to write this down as I'm saying it, it's going to be negative, it's going to be rho in the negative rho direction. As soon as I write that down, okay, so we have rho, A sub rho, and I'm going to explain in a minute why. And we have H a sub z. Now, stop talking to me. So, why is it negative? Well, because, think about it. Remember, in polar coordinates, it's always from the origin. So if it were in fact rho h, it would be a distance. The vector would look. I'm gonna undo this as soon as I do it. Let me put it in red or something. Red because it's wrong. It would be in this direction, starting from the origin, and then it would be up h. It would actually look something like this. It would be up like that, and that's not what we want. We actually want the opposite. If we saw it at negative rho, it actually, well, technically it goes this way and up. But if you remember, these are vectors, so you can translate the vector any way into any position you want. It doesn't have to start at the origin. So if we just move this over here, it'll be this vector. Yes, we could translate this guy too, but you can't rotate a vector. You can only translate it. That's why it has to be negative rho and up z. So it can be this. It can just move it to this one. Kind of confusing at first, but that's what it's going to be. And consequently, our magnitude, I'm just going to write it as non-bold r, is going to be square root by Pythagorean theorem of rho squared plus h squared. So if we have a sub r over r squared, that's going to be, well, this guy over here divided by this, and